Dear student, we are going to design stator of three-phase induction motor. Stator is a static part of three-phase induction motor. It consists of stator winding, stator core, stator teeth, then end plates, eye bolts, etc. All the stationary parts are called stator. Now stator winding, design of stator winding, and then we will go to design the stator core and stator teeth and stator slots. The design of stator winding. Stator consists of slots on its inner periphery, and the copper winding is generally placed in the stator slots. Winding is generally double layer type winding. Single layer winding is used in small rating machines. Most of the machines have double layer winding. Okay. And class of insulation is generally B, F and E class. The three-phase winding may be connected in stator or in delta. Now turns per phase. How to calculate turns per phase? Then we calculate the size of each conductor. The stator turns per phase. Turns per phase. This is T for turns, S for stator. Stator turns per phase. Now we have flux per pole maximum. So phi m is the maximum flux per pole. Maximum flux per pole in Weber. Now we have B average. B average, specific magnetic loading. B average is P phi m pi dl, or this is phi m upon tau into L. Tau is the pole pitch. This is pi d upon P. From this calculating phi m, maximum flux per pole, this is equal to B average, this is pi d upon P into L. Now we have stator voltage per phase. Let ES is the stator voltage per phase. Stator voltage per phase, and this is equal to 4.44 phi m f ts kws. Stator voltage per phase. This is counter EMF induced per phase. Assume that applied voltage and counter EMF is equal. This is 4.44 phi m f ts turns per phase and kws. Kws is the stator winding factor. This is you have to calculate from the formula kws. You have to calculate stator winding factor. Kws is Kc into Kd. Kc is coil span factor, Kd is distribution factor. Generally kws for design, kws is assumed 0.955. Then stator per phase, from this formula we get stator turns per phase. This is ES upon 4.445 m F into kWs. This is maximum flux calculated from this formula. Then kWs is the stator winding factor. This is assume 0.955. F is the supply voltage and ES is the stator voltage per phase. ES depend on the connection of the stator winding. If stator winding is star connected, then ES is equal to line voltage divided by root 3, and if it is delta connected, then ES and ES is per phase equal to line voltage. So this way turns per phase in the stator winding you can calculate. Now going for calculation of size of each stator conductors. So stator conductors. Stator. To calculate size of conductors, we have to assume current density. Current density is generally denoted by del. Del is equal to current density ampere per mm square. For three-phase induction motor, del is generally between del is between 3 to 5 ampere per mm square. Any value between 3 to 5 ampere per mm square you can assume for the design purpose. Then you have to calculate current per phase. Current per phase. This is I for current, S for stator winding. So stator winding current per phase IS. This is equal to Q. Q is the kVA input. This is divided by 3. So this is kVA input per phase into ES. ES is the 3-phase per phase applied voltage. So this is IS in kiloampere. You have to convert it in ampere by 10 raised to 3. So you get ampere. So this way current per phase calculated, and after that assuming suitable current density to calculate the area of each conductor. So area of each conductor in stator winding, this is AS, this is equal to current per phase divided by current density in stator, assume. So this is the mm square. This is area of the each conductor. Now if current is small, then round conductor is used, and if current increases, then bar or strip type conductors may be used. So this was about stator winding, turns per phase, and the stator conductor size. Now type of slots, stator slots. So stator slots are types of slots. Generally slots are complete open, and semi enclosed type, semi-closed type. So this type of slots, generally this is this type of slots are called semi-closed type slots, and this type of slots are called open type slots. So most of the machines, this type of slots are used, and these types of slots are used for small rating machine. These slots provides more uniform magnetic flux distribution from stator to rotor, and this type of slots have wider opening, so it influences the air gap, or you can say reluctance. At the same time, this have some more advantage than this type of slots. Semi-enclosed type slots are used in induction motor because pulsation loss is less and the quieter machine operation. Then number of stator slots. Number of stator slots. There is no definite rule to select slots, stator slot or rotor slot. There is no definite rule to select the slots, but there are some guidelines that we have to follow before selecting the slots. So guidelines to follow slots. Guidelines to select the slot. First guideline, tooth pulsation loss. Tooth pulsation loss. With open type slots, this type of slot, with open type slots, slots opening have considerable influence on the air gap reluctance. Slot should produce low air gap reluctance so that less pulsation loss will be there and the quieter operation will be there. Okay. Then second guideline is the leakage reactance. Second guideline, leakage reactance. This is due to leakage flux, leakage reactance. If number of slots increases, if we select large number of slots, so if number of slots selects large, yes, for slots, stator slots, large, then slots, large number of slots we have to insulate, large number of slots to insulate. Therefore, width of insulation increasing. Overall width of insulation is increasing. Therefore, leakage flux has longer path through the air. So, leakage flux decreases. And therefore, leakage reactance decreases, because leakage flux depend on leakage flux. Flux is decreasing, so leakage inductance is decreasing. Therefore, leakage reactance X, this is omega L. So as leakage flux decreases, leakage inductance decreases, therefore leakage reactance decreases. So we can conclude that as number of slots increases, leakage flux decreases, so leakage reactance decreases. So we can conclude that the leakage reactance is inversely proportional to the number of slots. So if number of slots are selected large value, then leakage reactance of the motor decreases. And as leakage reactance decreases, diameter of circle diagram increases. This is V upon X. Diameter of circle diagram is V upon X. So V is same constant. As X decreases, diameter of circle diagram increases, so that overload capacity of motor increases. So what is conclusion? Conclusion is that as number of slots increases, leakage flux decreases, leakage inductance decreases, leakage reactance decreases. Conclusion is that leakage reactance is inversely proportional to the slots. So if we select large number of slots, leakage reactance is less. Therefore, diameter of circle diagram is increasing. Therefore, overload capacity is increasing. So if we select large number of slots, overload capacity of the motor is increasing. Point number 3 is ventilation. This is point number 3. If D is constant, D is the one of the main dimension of the 3-phase induction motor. D is constant. D is inside diameter of the stator. So if D is constant and number of slots selected large, then slot pitch decreases. Slot pitch is pi D upon S. So if number of slots selected large, slot pitch get decreases. And if slot pitch decreases, slot pitch YS, denoted by YS, this is width of teeth plus width of slot. So if YS decreases because of large number of slots and constant D, WT, width of slot, and width of teeth decreases. Both decreases. So teeth become mechanically weak. So may be supported by welding on the ventilating duct. That affects the cooling. Then next point is point number 4, magnetizing current. Point number 4, magnetizing current. Producing magnetizing flux. No load current depend on this component. Magnetizing current and iron loss. Magnetizing current and iron loss. Point number 4. So we know flux density in teeth is directly proportional to B average. B average is specific magnetic loading. So if large number of slots are selected, if slots selected large, flux density in teeth increases. Flux density in teeth is increasing, so that magnetizing current IM, this is increasing, and as flux density Bt is large, iron loss in the teeth, iron loss is Pi, iron loss in the teeth is increasing, and therefore there is overheating of the teeth. So flux density in the teeth should not exceed beyond the limit, otherwise magnetizing current is increasing. At the same time, iron loss in the teeth is also increasing, so that current, no load current is increasing, and the iron loss, due to iron loss in the teeth get heated. Point number 5, guideline. This is guideline number 5. This is cost. This is cost. As number of slots are selected large, as number of slots selected large, then number of coils to wound increases. Number of coils to wound increases. Therefore, insulation increases. Each slot insulation increases. Okay, before putting winding in the slot, we have to insulate slots. As the number of slots increases, quantity of insulation required is increasing. Therefore, cost of insulation increases. So cost of insulation increases. At the same time, number of coils to wound is increasing. Number of slots punching, we have to punch more number of slots. Therefore, labor cost of the punching slots and winding the machine increases. As per guidelines, number of slots per phase per pole. So number of slots per pole per phase, this is denoted by Q. It should not be less than 2. Number of slots per pole per phase, Q, should not be less than 2. Then stator slot pitch, YS, YS is slot pitch, as it is for stator. This is stator slot pitch, YSS. This is equal to gap surface. Gap surface. This is pi d. Gap surface upon total number of slots, stator slots. Total number of stator slots. Gap surface is pi d. So YSS is pi d upon stator slots YSS. So number of stator conductors, total number of stator conductors, total stator conductors is Z for conductors, S for stator. This is equal to TS. TS is the turns per phase. multiplied by 2. So this becomes conductors per phase. Conductors per phase is multiplied by 3 for phases. So this is the total stator conductors and is equal to 6 TS. So from above calculation we have stator turns per phase TS. TS is multiplied by 2, so we get stator conductors per phase. Stator conductors per phase is multiplied by number of phases 3, so we get total stator conductors and is equal to 6 TS. From this, conductors per slot is calculated. Conductors per slot. This is conductors ZS, total stator conductors. ZSS is the conductors per slot. This is equal to total stator conductors divided by total stator slots, and this is equal to ZS upon SS. ZS is 6 TS upon SS. This is conductors per slot. Now calculating area of each conductor, now calculating area of stator slot, stator design, you can say area of stator slots, area of stator slots. So we have slot space factor, slot space factor, slot space factor SF, slot space factor SF. This is equal to conductor area per slot, conductor area per slot divided by area of each slot, area of each slot. So from this area of each slot, area of each slot, this is equal to conductor area per slot, conductor area per slot upon slot space factor SF. Also area of each slot, this is equal to, this can be calculated like this is equal to ZSS, area of ZSS. ZSS is the conductors per slot, stator conductors per slot into AS. AS is the area of each conductor. So ZSS into AS, this is the copper area, conductor area per slot upon slot space factor SF. Thus SF is lies between 0.25 to 0.4, 0.25 to 0.4. After slot area, decide, after slot area deciding deciding the slot dimensions. Slot dimensions, that is width of slot and the depth of slot. Slot dimensions are width of slot and the depth of slot. Generally, width of teeth is taken equal to width of slot WS. Slot should not be too wide. If we make slot too wide, WS will be more for same slot pitch YS. If WS is more, then WT will decrease. Width of teeth will be decreased so that teeth will become thin. So slot should not be too wide. So at the same time, WS, width of slot WS is adjusted. WS is adjusted such that flux density in teeth should lies between. You have to adjust WS such that the flux density in teeth should be between 1.3 to 1.7 Weber per meter square. This is important. Flux density in teeth should be between 1.3 to 1.7 Weber per meter square. If BT exceeds, if we select wider slot WS large, and BT, the area of teeth will decrease and the flux density will increase. So flux density in teeth, if exceeds 1.7 Weber per meter square, then there is more iron loss in the teeth. Now generally ratio depth of slot is to width of slot. This ratio lies between 3 to 6. So this way, from this we have to determine the slot dimensions WS and DS, width of slot and the depth of slot.